That's what happens when you have something that's solid, right? Versus something that's doesn't have a high intermolecular attraction. So the molecules are actually pulled further apart, right? They don't want to stay together, like in a solid state. Okay, so on our next slide, this talks about kinetic energy. And so on your worksheet that I gave you, that was that one, just that one-sided one. I think the very first question. Let's see.
That temperature does all kinetic activity matter cease?
There we go. And there it is. There's your answer right there at absolute zero. The kinetic energy is zero. I think that's on the very next one too. I think it's on the other one too. Yeah. So it is 0 Kelvin. 0 Kelvin. I'm just gonna leave this out right here on my desk. Just might want to reference it again. All right, so when we talk about, did we jump ahead? Thank you. I was like, oh wait, something happened. So the key here is the higher the kinetic energy, yeah? Okay, so the more kinetic energy that you add to something, the more likely that the material or the matter or whatever you're working with will exist as a liquid or as a gas. So something can already have high kinetic energy, or you can add kinetic energy. And how would I add kinetic energy? You increase the temperature. Very good, Jordan. You heat it up. That's the quickest way that you can add kinetic energy, is to heat it up. So I wasn't too far off when I said light it on fire, right? And no, I won't sing the song, even though I feel like singing the song. My husband hates it when I do that. He's like, that's so dumb. We all know the song. Light it up, light it up. I love that song so much. He thinks it's dumb. I don't know why. I don't know how you not like that song. But anyway, I digress. Okay, so if something is cold, it has no kinetic energy. But if something is hot, right, it has a lot of kinetic energy. Okay, so and then the more you heat it up, the more kinetic energy that it has, right? Okay, now let's look at intermolecular attraction. So the higher the intermolecular attraction, the more attractive forces that it has, the more likelihood that it will be a solid material, because solid materials are like interwoven molecules, and they even look like a block, right? They even look like a cube, right? So they're all the molecules are in line with each other. And there's a picture of one on the very next slide where you can see all those molecules like lined up like a little box, right? And so they are very tightly woven together. They have a very high intermolecular attraction, and the molecules are even in order, right? They're in very fixed positions. So this is what a solid would look like. So it would take a very high amount of kinetic energy to break that bond, okay? You can't, they don't want to pull apart from each other, which is why they exist in a solid. So everything in front of you, right here, like again, your desk, your cup, right, your binder, all these things, right? It would take a lot of kinetic energy to be able to break apart that high intermolecular attraction. Now, your paper, not so much, right? You could actually easily, I mean, that wouldn't, we were burning leaves this weekend, and I'll tell you what, whoosh, that thing, like, right? It's actually kind of fun to watch, unless you're an asthmatic, and then it's like death in the pie. I'm like, oh, Kenny, away from that. But it is fun to watch because they don't have a very high, the leaves don't have a very high intermolecular attraction. They just go right up, right? Nobody else burning leaves. Do you get that? No.
I didn't even know you burn leaves.
Yeah. Well, you have to do
You
something
just
with
put
them.
them in the bags. And
Well, I mean, I guess if you're not in a place where you can burn, we're in a place where we can burn.
Okay.
Yeah. So that would be. I don't even know how many billion bags we would have.
Wow.
We have a lot of stinking trees, and we have a lot of land. Oh my gosh. They don't want the bags.
Get those great kids busy.
Tell you what, I was watching my neighbors. We had breakfast and we were standing outside. My husband's like, man, I tell you what, our neighbor were out there. They had all their kids outside. One was blowing, one was driving the mower. He's like, one boy's just standing around, you know. But he had like all 4 of his kids out there, and I was like, where's our kids? I'm calling our kids right now. Get over here and help your father. He's old. We're out there doing it ourselves. I'm like, I'm dying. My back hurts. It's way too much work for 2 old people. Kids, our kids never helped. Punks. Lazy. Even when we pay them, they didn't help.
Oh, shit.
I have to keep kicking them. Get back to work. I'm paying you. Kids. Then yeah, I should call my great. No, they wouldn't do it. They want to play in the leaves. Okay. All right. Let's look at what sort of qualities liquids have. So liquids, now they're not in fixed order, right? Their molecules are not in a fixed order. They're sort of sliding around each other, right? Because liquids will take the shape of their container. So whatever container you put them in, they're going to take the shape of that container. So if the container is, you know, like an S shape, right, it will take the shape of that container. And the molecules move around each other. But they do have very strong cohesive forces. And they're constantly moving. Now, we talked about this in lab, how we can have like molecules in liquids, or we can actually have unlike molecules in liquids. So you can actually have either cohesive forces, or you can have adhesive forces. And remember that I drew the cylinders, right? And then I had a cylinder that had you had a cohesive force, or you had an adhesive force. So this one was adhesive. Okay, and I always think of like adhering to the sides of the container, okay, versus cohesive, where it is like coupling together and trying to what's the word I'm looking for? It wants to occupy the smallest space possible, okay? So this would be like mercury. Again, mercury does this, blood in our body does this. Like it's a very dense material, has a very strong cohesive force, almost like it's very viscous, right? Very viscous. And even surfactant in your body will do this, okay? Now, adhesive is more like water. Water is a very adhesive force. Now, we're going to talk about water here in a moment when you add something to it, okay? So, when we're talking about this cohesive sort of shape, we're talking about the surface tension, right? There's very high surface tension on here, right? So you could almost just stand on this, right? Because the surface tension is so great, okay? Now, water, you can have some surface tension there, but not the same as this, right? So we're talking about surface tension from all sides, right? Creating this force. Now it depends on, you're going to have surface tension right here, right? And at this point right here, but you're going to have surface tension creating all from around all sides here at this cohesive substances, okay? Because there's an attraction from all sides of there, okay? Does that make sense to us? Kind of? Can you see that? Kind of. Okay. Okay, so when we talk about gases, so now we're looking at some totally different intermolecular attraction. So there really is no attraction when we're talking about gases, because they're always in random motion, okay? They're not knit together, right? Their molecules are just randomly in motion. Even when when it's cold, they're still in motion. They're just moving very, very slowly, okay? Unless they're at 0 Kelvin, and then there's nothing happening, okay? but they are still moving. And when they get heated up, now they're really in a very, there's a lot of movements. They're just banging around each other, right? So that's actually where that force actually comes from, because of those random collisions. And that's where the pressure actually is exerted from, is from the molecules actually bumping into each other. That is the pressure that is exerted, is from those random collisions. So they have a very high kinetic energy. So of all of the three states of matter, gases have the highest kinetic energy, okay? So that is an important differentiation to make, okay? So they have the highest kinetic energy. Remember that solids have the highest intermolecular attraction, so that is what makes them different. And then liquids have the strongest cohesive forces. So there's a lot of sort of unique things about all the different states of matter. Now, the other unique thing about gases that's appreciable is that they can expand very readily, and they can also contract very readily to occupy their container. So liquids will move right freely, and they will take the shape of their container, but they're not expanding and contracting, okay, the same way that gases do. Now, if you heat up a liquid, if you add kinetic energy to liquid, like we talked about putting water on the stove and boiling it, right now it's going to turn into a gas, right, that will now do this, right, and expand and contract to occupy the container. So when you add energy and you change now the state of matter, right, now you have something that will expand and contract to occupy the shape of the container, okay? But a liquid itself won't do that, okay, unless you change the state of matter, okay? Because if you cool liquid, you freeze it, what does ice do? Does it expand or contract? It expands, right? So you have to be careful with that. Now, what about soda cans? Right, they're enclosed, right? So they're closed. What if you add heat to that? So what if they're in your car, right, on a hot day? They expand and they actually explode, right? Now, part of that is due to the gas, the CO2 that's inside of the can, but it's also because the gas is enclosed space, okay? But it's also due to the fact that is enclosed, that liquid's enclosed, and it gets hot, right? So then it will actually expand right out of that container. So there is some appreciable differences there as well, okay? But solids don't do any of those things, okay? Unless you change the state of matter by adding heat to a solid, right? And that would be to change it down, that you have to actually burn it, right? And does it even then change the state of matter? What does it change to? What is a solid? Does a solid change the state of matter when you burn it?
Yeah. I mean, liquid or like ice, if you like, because that's a solid and you burn that, then yeah, because it'll turn it back to a liquid. Or gas.
So that would be a liquid, but
So
what about a
ash?
solid? It turns to ash, right? So are you changing the state of matter necessarily?
No,
No,
like,
because it's still solid.
Right? But not if you heat it up hot enough to where you actually like disintegrate it. I mean, then are you changing the state of matter?
Yeah.
It's gone. Poof.
Cremation.
Cremation.
What if you heat up like sand? It turns to glass.
Yeah. Yes.
But then you have
That's
don't you
really
have to-
cool.
don't you have to have pressure?
Then it becomes actually liquid.
Yeah.
For a moment in time, it
Before it
becomes
hardens.
liquid, and then it hardens back again, doesn't it? Yeah. That's very cool about glass. Like glass blowing amazes me.
Yeah, I like
That's
watching
super
videos.
cool. Yeah.
Is
Yes.
that a Facebook video?
What?
You can watch it on Facebook. Yeah. Yes.
What did you mention when you were like, gases has the highest kinetic energy out of all three, and then you
I
said,
can't hear strong.
what did you say about liquid? Because you said something specific about each one.
Liquids, they have the highest cohesive forces.
Cohesive forces. Okay, thank you.
Yeah. All right, okay, are we gonna go on to our next one here? Okay, all right, so there's some more things about gas that are really important for us to understand. Some of these are new words for us, maybe. So we talked about how gases expand, right? And this would be due to increased pressure. So like if our cylinders, our tank cylinders that we have gases in, like our oxygen tanks, if they were to get hot, right, if they were to be in an enclosed space and they were to get too hot, they could actually, they could combust. Like if an oxygen tank was in a fire, it could actually combust. But first it would actually expand. And that's actually why our oxygen tanks have an expansibility property on them up to 200 psi extra, right? They have the ability to be able to expand up to 200 psi. Now that may not be enough if they're in a fire. Obviously that wouldn't be enough to prevent that. But they can also, if they get cold, right? They can, there's an expansibility property if they are to get too cold. Now they also, gases can also compress, again, from increased or decreased pressure, they have compressibility. But they also have diffusibility. Now this is something that I think that we just don't think about it, right? Because gases can diffuse. And what direction does diffusibility move from? High concentrations to low concentrations, exactly. So everything always moves from high to low, right? Until it reaches equilibrium. Right, good. Okay, and then gas is also liquefiable. So at critical temperatures and pressures, it can actually be liquefiable. And we learned this. In what way do we learn this? That gas can be liquefied. Oxygen in our fractional distillation process. If we compress it, right, and then we cool it, now it becomes liquid oxygen, and then we can store it cryogenically, can't we? So all of these things right here, all these qualities of gas, that is really relates right back to our fractional distillation process, doesn't it? Right? And that's kind of cool, like how we can actually do that. It's pretty amazing, right? Okay, let's take a look at fluids. Okay, so still staying on liquids and gases. So we talked about how liquids can flow, right? They're capable of flowing. Now this would be all liquids. So in lab, we looked at several different liquids. We looked at honey, we looked at like dish soap, we looked at corn syrup. So lots of different liquids that had different properties of viscosity, right? So almost at like thickness, right? Okay. And how they will also conform to their container, right? So they will, whatever shape the container is, they will take that shape, right? And pressure exerted on them, it doesn't even matter, right? It will exert in all directions of the shape of the container. Okay, so no matter what shape the container is, it's going to exert pressure on all sides of the container. So no matter what shape this was, or if this was this container, it's very squeaky, looked like this, right? It would still exert pressure on all the sides of the container equally.
You just drew a nice dress.
Oh, I did. I should put some arms and legs on it. I didn't even, yeah. It's a little low cut for me, but that's fine. Okay, so our next slide is going to talk about changes of phase. Okay, so this was the term latent heat, and this was what was on our lab packet. Now, I thought about bringing in one of those, what are those called? Those like little, it's like a little single burner, right, that you can, what's it called? Like, not a Bunsen burner, but like a
little stovetop one?
like a little stovetop, like, yeah, where you just could have like in your camper or whatever, like a little, like a little single, a hot, yeah, hot, what'd you call it?
Hot pot.
A hot pot? I don't know.
plate?
Yeah, a hot plate. Yeah, like a little hot, yeah. And I was like, no, that's gonna be, someone's gonna burn themselves. Someone's gonna hurt themselves or burn themselves or set something on fire. I was like, I don't know how this is gonna go. Because I know my sophomores would definitely do that. They would definitely light something on fire. Like, I could tell you probably who would be too, so.
I know who would be too.
So anyway, but it would be cool to see this, and we could use we're gonna use the microwave on Wednesday. It's a little safer.
Are we sure?
I don't know, but I'm gonna take everything metal out of the room. But we're gonna talk about how when we apply energy, right? When we apply heat, so energy in the form of heat, right? Kinetic energy, we're going to be able to change that phase of matter, hopefully, right? And we will be able to. But again, when we add or we take away heat, that's how we can change that phase of matter. And we all know this, right? But we actually call this latent heat. So that is the amount of heat, right? So how much, the degree of temperature change, the amount of heat that we actually need to change the state of matter. Okay, so whether we're adding heat or we're taking away heat, that is the amount of heat that is needed, the amount of kinetic energy that is needed to change that phase of matter, either back to a liquid, to a gas, back to a solid. It goes both ways. So latent heat is the amount of heat that is needed to change that phase of matter, okay? Because as we increase our temperature, we increase kinetic energy, but it also weakens the bonds. So that's an important thing to remember, okay? So not only does it increase the kinetic energy, but it does break those bonds, okay? Because when we think about solids in particular, remember that they have that strong intermolecular attraction. So when we add heat to that, we are breaking those bonds. We're increasing kinetic energy, but we're breaking bonds, okay? And again, if it's a large enough amount of kinetic energy, we're going to go from a solid to a liquid to a gas, okay, depending on what our state of matter actually is. Okay, questions about that? No?
You said the latent heat is the amount of heat needed to change the state of matter?
Not just heat, it could go either direction. It's the amount of energy or temperature needed to change the phase of matter. Because it could be cold too, so it goes back and forth. You're just changing the phase of matter. So the amount of energy, the amount of temperature. All right, so we're gonna go on to 2. Woo! Okay. Hopefully it doesn't, you're fine. Hopefully it doesn't want Use it like so. All right. This should be also on your worksheets. Lecture 2 now. Lecture 2. Oh my goodness.
Tell her to send me one answer key out of the binder. Where is that one?
I would never.
You got an answer key?
I told her, I said, send me pictures of all the answer keys.
Oh.
Because I'm sitting over here.
Answer keys are right here.
Good to know.
Right.
Now I know which one to go for.
That's right. I mean, there's a lot of power in that seat, but this is
That's the Bible.
this is the Bible right here. Okay, all right, we're gonna go back to our gas laws. They're back. They're back.
They are. They never left.
They never left.
Professor Staples said you love.
We were just putting our toe in it a lot.
I love doing the laws. I love doing the laws. She hates doing the laws.
That's what she said.
Yeah. She doesn't like teaching the theory stuff, but she doesn't like it. She's like, oh, I'm glad you're doing that. She doesn't mind Boyle's law though, but okay. So these are our gas laws. So 1, 2, 3. I'm missing one. Boyle's law, Charles' law, Gay-Lussac's law. Oh, maybe not. Temperature.
I think that's it.
Gary's law.
Gary's law. You just
Graham's
making up
law,
stuff.
Henry's
Graham.
law.
Well, there is a Graham's law.
It's like 40 laws.
There is. There
Fick's
is.
law.
Oh, fix? Did you say fix? Do you want to learn fix?
No, we already
Oh,
started.
I say what? There is a
If
fix
you want to teach us
equation.
fix,
No, we
you
are.
can because we
Get
have
it
it for
go
her
with
class.
it.
But if you want to teach them,
You have to do fix.
Yeah,
Yeah.
Fix is cardiac output.
yeah.
Yeah.
Fix.
Fix
You're
it
doing
and
fix.
Graham.
Henry, there's the Henry.
I think
Graham.
Graham too.
Graham.
And Graham.
Why is she teaching you fix?
And the law of
That's what
I don't
For
know.
cardiac output?
menopause, whatever it's called.
You
law
don't
of
want to go
applause.
there.
All of the laws.
You're lucky I'm on meds and I don't have any more hot flashes. Ooh, I'd be up here. Is my hair on fire? Oh my God. The students are like, shh, nobody talk. She's scary. I'm shocked. I thought I was the one that brought you Vic.
You can teach us fix.
I mean, I'm all about
She
it.
said she hates the laws.
I like thick. I like thick. All right, woo! Boyle's law. This is probably one of my favorites. I feel like. Okay, so remember we have 3 variables, right? Volume, pressure, and temperature. Okay, so when we're talking about these, remember that one is always going to be constant, held constant in the equation. So then you're trying to figure out which one am I working with, right? So if you don't see it, it's constant, okay? And then you're always going to say, but I don't remember you were asking me, how do I even know what I'm doing with these word equations, right? This is practice, okay? So, I know, and we're going to do some practice, okay? So, in Boyle's law, remember this is the only one that's inverse. This is the only one that's inverse. So, one goes up, one goes down. One goes down, one goes up. All right, so this is the inverse one. So, again, it's helpful then to write off to the side T constant or temp constant, however you want to write that. Okay? So, what Boyle's law is V1, P1, V2, P2. That doesn't always make sense to me. I'm like, well, where's the twos? Huh? Right? You're gonna see it different ways depending on what books that you read, okay? But I just know I'm starting with one volume and pressure, and I'm gonna be getting a new volume and pressure. That's how I like to write it, okay? All right, what's our next one? Inverse, right? Okay, so, ooh, that was fun. Look at that big old, ooh, I think that'd be fun to do, right? Like, yeah. So just remember that, right? If you're the volume and pressure, right? So if volume goes down, pressure goes up. And this is the best clinical application for this is to think about when we are flying, because as respiratory therapists, we will fly in helicopters with patients. And if we have an intubated patient and they have that endotracheal tube in, there is a cuff on that endotracheal tube and it has a volume of air in it. So if we go up in the atmosphere,
You gotta deflate that cuff a little bit.
we go up in the atmosphere, okay? So the pressure, we go up in the atmosphere, okay, which equals a decrease in pressure, okay? That means that there will be an increase in volume on the ETT. Ah! I'm gonna blow that cuff, right? That is the best example for you for this law. So if we go up in the atmosphere, that means the pressure goes down, right? The pressure goes down, which will cause an increase in the volume on the ETT, the cuff on the ETT. Let me write that, right? On cuff, on ETT. Does that make sense?
That little, when we remember that cuff, that little like balloon, not
Yes.
thing, but it's like that clear thing that was around
It's a
it.
balloon,
Yeah.
yes, okay? So the
Because
volume in that cuff will go up, which can make it rupture, or it can cause damage to the mucosa of the airway, of the trachea. Usually it'll rupture, okay? And now you're in trouble. Now you're not gonna get any volumes, any pressures to your patient. You're in trouble. And you don't wanna be intubating in a helicopter. Lord help you. Baby Jesus, help you. Okay? Help the patient. All right, so that is the best example. Okay, so now you have to do something, or you have to bag mask the patient now the whole rest of the way. Again, baby Jesus, help you. All right, you're in trouble. Okay. Okay, so that's the best example of this one.
What does the numbers mean though up there? Like the V1, P1, V2? Was it
So
two?
glad that you asked that, Sherelle. It's a great question.
Oh.
Let's look at what it means.
Oh.
Okay, let's do it. Yeah, okay. All right, so this is an example of what you might see. All right, so your starting volume is 50 mils. That's your V1, 50 mils. All right, I had 50 mils. Okay. And I'm at a atmosphere of 760 millimeters of mercury. That's my starting pressure. That's my P1. Okay? P1 is 760 millimeters of mercury. You're going to need a calculator or your phones. Yes, you may get your phones out. I know none of you had your phone out right now. You're so good. Good job. Nobody did, right? Nobody did. Okay. How could you? You're paying too much attention. All right. Now I'm telling you that I'm going down in the atmosphere. My pressure is changing. And I'm going down in the atmosphere. My new pressure is 760.
Your new pressure?
My new pressure is 700. Whoopsies. Is 700.
So would that be P2?
This is my P2. And I want to know, what's my volume going to be?
X.
Yep. What's my volume going to be now? I don't know what it's going to be. That's my new volume. I have no idea. It's going to be my X. So you can put V2 if you want. You can put X. I'm actually going to write X here because that confuses me. I need an X because of algebra. But that's what's going to happen. That's going to be your P2. So all you're going to do, you're going to multiply these together. Now you're just doing an algebra equation, right?
What's your P2?
We don't know.
I mean, what's the P1?
P1 is the 760.
This is your V2. This is your P2. I don't know what my V2 is. That's what I've got to find.
Okay.
That's what I've got to find. Okay? So this is just algebra now. Multiply these two together. So you need a calculator.
Hold on, you said that is your that is the P2?
Yes.
Yes.
We don't know the V2.
Yes.
I don't.
Okay.
This is P2 because it's a pressure.
Right, okay.
It's a pressure. This is why we reviewed pressure units of measure. And this is going to be my V2. I don't know what it is yet. Okay? And if you'd rather write this as your V2, go ahead. That's fine. You're going to write it as that at the end. All right, so what's 50 times 760? Somebody have that?
38,000.
38,000. Beautiful. And now you have 700 over here. X. Now you're going to divide by 700. You're going to divide by 700. Someone please tell me what X equals.
54.28.
54.28.
ml.
Thank you. And that is mLs. That's right, because it was mLs over here, right? And it's going to be mLs over here. And that's what you were trying to find, was what your V2 was. So this is your new volume. And it makes sense if you go back and you look. If you go back and you look, the pressure went down. The pressure went down, so the volume should go up. And the volume went up. It was 50, and now it's 54. Check yourself before you wreck yourself. That's Boyle's law. Okay? Oh, lovely. There's our answer.
I know, I just looked at that.
Yay! Good job over there.
Thank you.
Okay. Yeah, don't look ahead or you're gonna. Don't peek. No peeking. All right, try your next one without looking. You're gonna set it up the same way. You found the stamp.
I was gonna stamp my paper, but
See, that's cheating.
I found benefits.
Like that's a lot of power over there. That's that stamp. She's like,
Power crazy over there.
I am. I'm like, is this the stamp?
I've been noticing an acting
I've
difference
been
since the
acting
other day.
different.
it's been acting different since she's been up there.
Yeah, ever since the other day, I don't know.
Got to be someone else next time. Freaking this thing better get fixed. Okay, all right. Did we get about 380?
Yeah.
Good. Okay. All right. So that's how we work with Boyle's law. All right. And Boyle's law is important for us for a lot of things. Not only does it explain these atmospheric changes, how then volume is affected by atmospheric changes, like volume we talked about in our endotracheal tube cuff, right? It explains how people get air embolism, like if they are diving, right, and they come up too fast, that's what the bends is. But for us, it is the concept of mechanical ventilation. So when we talk about pressure, how these changes in pressure are changes in volume. So when somebody has, they're experiencing high pressure in their lungs, when we're trying to ventilate somebody and they have a very stiff lung and it is causing very high pressure, that means that we're not going to get much volume into those lungs. So when they have ARDS, when they have pneumonia, when they had COVID, right? So we were having, it took a lot of pressure and then we were getting very small volume changes. So it really describes that whole theory of mechanical ventilation. It would require tremendous amounts of driving pressure and then we were still only getting very low volumes. So that is the whole concept of mechanical ventilation. So you're going to be learning lots more about Boyle's law and hearing me say it a lot more when we get into our concept of mechanical ventilation topic, which will be happening at the end of this semester. A little bit, just a little bit. We're going to peek into that too. So, okay, our next one is Charles' law. So let's look at Charles' law. I'm going to erase here. All right, so Charles' law. So this one is pressure is constant. So P is constant here. Okay, so now we're dealing with volume and temperature. So remember I said that temperature always goes on the bottom. Okay, so when you're setting these up, temperature always is gonna go on your bottom. So you've got a volume, okay, over a temperature, and then you've got a new volume and a new temperature. All right, so always put your temperature on the bottom, and then you'll never make a mistake in your math, okay? Now you can do this math a couple different ways. I like to teach it in a way that we cross multiply. I just feel like that's the easiest way to explain it. But yes, you can set it up a different way if you'd like to. So if you don't like my way, that's okay. All right, you can do it. You can do it the other way. But I'm going to show you how to cross multiply. All right, so there is a direct relationship here. So if volume increases, temperature increases. If temperature decreases, volume decreases. And we talked about a balloon in this sense, where if you take a balloon outside on a cold day, the volume is going to shrink inside that balloon. I think I've got a picture of a lava lamp, which I think is kind of groovy. Right? So whoever did you ever have a lava lamp? Yeah, right. And they got hot, right? When you turned them on, they got hot. So nothing was ever happening in the lava lamp. You had one too? Oh.
Yep.
All right. Right. So as soon as you turn it on, well, she's so young. I was
That's
like,
why
I didn't know
I
if you
asked her.
were
I'm like,
thinking,
you know what
yeah.
that is.
I know. I was like, all right, girl.
Yeah, like,
I
yeah.
you just don't make them. I don't know, but because
They definitely
they always cause fires. Like they're dangerous. Actually, don't leave it on. Don't get it near like anything.
Yeah,
Can't
it
be
still
near
does
your.
have like that warning on the inside
Yeah,
of the light.
like don't put it near a curtain or anything. Like for real, my son's a firefighter. Like I have to say these things. Yes.
Have you seen the one where the bird goes into like the water or something? Like
Oh,
it.
like tips its head.
Yeah,
Its beak. Yeah.
yeah.
Picks up a little water. It's like the
Oh
bird
yeah,
you
yeah,
saw
yeah. And it like
Yeah.
tippies.
Yeah.
Yeah, I have seen that one. I was like, what bird in the lava lamp?
What?
That's what I thought she
Yeah,
was.
that's all I was talking
Like,
about.
I gotta get that. So as soon as you turn it
Your son would
on,
love that.
yeah, the oil or whatever is inside gets hot, and then these little whatever they are, it's like I don't know, it's two cohesive forces. That's what it is, right? So there's a whole surface tension thing going on in there too, pretty cool. And then they get bigger. So the temperature increases, so the volume inside of that little bubble increases. And when you turn it off, then it goes away and then they all float to the bottom, right? So that's what's going on. So you heat it up, that whatever this little thing is made of, that gets larger as it gets hotter. So that's why I use the lava lamp in there. So, okay, so we've got a couple of it, and then we've got a hot air balloon, same thing. Okay, examples with our Charles law. Okay, so we have a starting volume of 100 mils, and if it helps you to write your unit of measure here, go ahead and do that while you're practicing, because then this is how you're going to know what unit of measure to finish with. All right, so I had mils here, and then my starting temperature was 273 Kelvin. Now, my new volume is what I don't know. That's where my X is going to go. But what I do have is my new temperature of 373 Kelvin. All right, so I'm just going to cross multiply this. Okay, so 100 times 373. That's a big number. 37300. Add your zeros. And then I've got 273x. Okay? Easy peasy, right? Okay, and then divide it out to get your x to stand alone. 273. So now your x.
136.
And this is your mils, right? What'd you get?
136.63.
136.63, and this is your mils, right? So this is your new, that's your new volume. 136.63. Are we right? Did we check ourselves? Ooh, and they just rounded it to 137. That's fine. You can leave it like that if you want to, or you can round it if you want to, and that's fine. And again, let's check ourselves. So we had, remember this is a direct relationship. So the temperature went up, right? So the volume should do what? Go up. Did it? Oh, it did. Woo! We're so smart. Look at us. Look at us. doing gas laws up in here. Woohoo! Look at you guys. So proud of you. Okay, we have another one. Let's do the other one. Try it on your own. Don't peek at the answer. Set it up on your own. You have a starting volume of 100. Starting temperature, oh, it was the same. And now you're just flipping it. Now you've got a new volume and you don't have a new temperature. Still cross multiply, if you like that. Not, I'm sorry. Do it your own way.